Okay, so hello everyone. I'm Daniele Manzoni, PhD student at SNS in Pisa, and I'm going to tell you about Lyman-alpha feedback at Cosmic Dawn. So, so why should we care about Lyman-alpha feedback? Well, if you have a massive star which drives its own H2 region, Lyman continuum photons are reprocessed into Lyman-alpha photons by the H2 region, and then we have heard that Lyman-alpha is a restaurant line, so Lyman-alpha photon will scatter many times into the neutral hydrogen gas. And this actually can impart quite significant momentum to the gas, and we think usually in terms of this force multiplier, which tells you the enhancement of the total force with respect to the single scattering limit. And in this plot, for example, is shown the total force multiplier for a uniform cloud, uniform setup, as a function of column density and metallicity. And as you can see, it can be quite high numbers, so a few hundreds for the most dense and metal-poor environments. And here instead is shown the relative contribution to the total radiation pressure. And again, you see that in dense metal-poor environments, Lyman-alpha radiation pressure can be the dominant source of feedback. And where do we find high density, low metallicity environments? Well, at high redshift. And this can be particularly relevant, for example, in the context of enhanced star formation at high redshift. And this is related to the problem of the overabundance of bright galaxies seen by JWST, which we have already heard about this week. And in that framework, you can have enhanced star formation just because if you have a very dense cloud, the free fall time is shorter than 3 mega-years. That is the time in which a supernovae explode. And then it has been shown that direct UV radiation pressure and the dust reprocessed infrared radiation are actually not able to stop the collapse. And in this framework, actually, Lyman-alpha is missing. And another environment again is a POP3 star, right? So where we have a super dense environment and metal poor. So, for example, can actually Lyman-alpha prevent the recollapse of H2 region or the trapping of H2 region around POP3 stars, or how it relates with accretion on them, and can this affect the IMF? So let's first have a look into star formation, and we can think of this framework in which we have our cloud, the massive stars form, and actually the H2 region will be driven by Lyman-alpha radiation pressure on the neutral shell just around the H2 region. This will drive very rapidly expansion of the bubbles, and then they will overlap and collide, and possibly even you can have star formation triggered by colliding shells. To put these in equations, we can simply describe the evolution of the shell just by momentum conservation, and this is the Lyman-alpha force on the shell, which depends again on the force multiplier and depends. Yeah.
Did you define Q? If not, what is it?
Oh, sorry. Yeah, Q is the volume filling factor of the bubbles. Total volume filling factor of the bubbles. Yeah. So with this, this has an analytical solution, which is a power law, and given the expansion of the bubbles, we can put in an equation for describing the evolution of the the global volume filling factor, and relate this to the star formation rate in the cloud. And if we parameterize the star formation rate in this way, we can actually solve the two-coupled equation and then get the star formation efficiency evolution. And here we are just plugging in this parameter lambda, which tells you the positive or negative feedback of the bubble expansion or star formation. If lambda is positive, this means that as bubbles grow and collide, they can trigger star formation, so you enhance star formation. So solving this equation, this is what we get. So here I'm showing the final star formation efficiency as a function of the surface density of the cloud. We are fixing the mass to 10 to the 6 solar masses. And so let's go first through the case in which lambda equals 0, so constant star formation rate. And this is this line here. And you can see that basically, even for very massive, very dense clouds, 10 to the 5 in surface density, the star formation efficiency is less than 5%. Then we can say, okay, maybe we can allow for positive feedback, and with this value lambda, which is derived with, by some assumptions on the effect of triggered star formations, and we try to get the most optimistic values we can get. And so this line shows the case of 2% metallicity, and actually the shadow region shows the scatter that you have due to metallicity, because dust can destroy Lyman-alpha photons, and so the higher the metallicity, the lower the force multiplier. But again, you can see that actually you don't have, in any case, really feedback-free star formation with order unity star formation efficiency because of Lyman-alpha feedback even at solar metallicity. And even more relevant, for POP3 you would have really very low star formations. So this is very simple modeling. Can we go further? Can we actually model Lyman-alpha? Can we do Lyman-alpha radiation hydrodynamics? Well, it sounds a bit crazy, but under some assumption you can do it, and this is what we are trying to do with the Lydion code. Lydion is a project led by Olof Nebrium, who is a PhD student in Stockholm, and we are trying to address the problem of performing Lyman-alpha RHD simulations. Of course, we start from the 1D case, and this is the Lyman-alpha relative transfer equation under the diffusion approximation. It's quite involved. I'm not going through all these terms, but basically, you can once you discretize it, it's basically you have to solve a three-diagonal matrix problem, both in space and frequency, and this can be done quite efficiently with the ADI methods. And basically, you can solve the radiative transfer of Lyman-alpha, of course, much faster than standard Monte Carlo methods. So we couple these with the hydrocode, 1D hydrocode. So we perform the 1D Lyman-alpha RHD. And here I'm showing the case in which we're putting a POP3 star at the center of a uniform cloud. And so here is the radius, and here is time, and the upper plot is number density. And on the right is the case in which you don't put Lyman-alpha feedback. So as you can see, you have the expansion of the H2 region, and then the H2 region recollapses because of the very dense gas and because of gravity. But instead, if we consider Lyman-alpha feedback, you can see that H2 region actually doesn't recollapse and breaks out. And here is the same, but for temperature. So this is, of course, very simple show test case, but I think it's very interesting because it can really have an impact on POP3 properties in general. And these also can be applied so this is actually to show you the force multiplier we are getting, and in this case you can see it's quite high, right? Order 50, 60 throughout all the simulation. And this can also be applied to higher metallicity, relevant for higher redshift universe. For example, he has 1% solar, and this is a case in which the H region anyway is expanding, but if you see that if you add Lyman-alpha feedback, the expansion is much faster, and we are kind of finding what we found with the simple shell semi-analytical model. And so this can really have an impact also on star formation efficiency at high redshift. So just to discuss and conclude, to make some points. So Lyman-alpha radiation pressure is really crucial for POP3 and high Z star formation because we have metal poor and very dense environments where Lyman-alpha feedback should dominate. And so the final idea, super goal, would be to go for 3D Lyman-alpha HD simulations. Of course, it's super difficult, and maybe so with some Lyman-alpha GPU supported code, maybe that would be possible. But with our code, actually, we are trying to go further. So we are now developing also GPU version for the 1D code, just to have a very efficient exploration of the parameter space. And then we are trying to go 2D, and maybe step by step we can go further and further, and we'll see. But yeah, just to conclude, so I want to point out that feedback-free star formation at Arashi is really not possible, because you always have Lyman-alpha feedback, and Lyman-alpha radiation pressure can actually prevent the trapping of H region around pop-3 stars. And so I'll leave with this, and thank you.
Great, thank you. We have some time for discussion. So,
thanks for the nice talk. I have a question, because, like, as I showed my slide, kind of like the number of scattering is depending on the Mach number at the same column density. So I just wondering, in your diffusion equation, so when you run the simulation, if you change the Mach number of the gas, so how it affect the feedback process in the Lyman-alpha?
So we are not accounting for that in this equation, but so actually we are so in this plot, this is the Ralf for uniform setup, and actually this includes kind of turbulence modeling of the effect. In a sense, it's not microturbulence. It's not really what you're doing with the proper turbulence. It's just saying solving the equation for Lyman-alpha radiative transfer. Let's say dividing fluctuations on higher scale and on smaller scales, and then with some math you can actually derive an effective equation for Lyman-alpha radiative transfer, and this gives you you can derive from that the force multiplier, and is included here. As a rule of thumb, we find that as long as you are around Mach number 10 and not much higher, the effect of the force multiplier is a factor of 4 or 3. So it does matter, but not drastically. Of course, I would be super interested to know what your box, what your turbulent box finds for the force multiplier, right? Because that would be super nice to have also comparison with these simple analytical estimates of turbulence and proper turbulent boxes. Yeah.
Very interesting talk. Oh, sorry, I turned it off.
Very interesting talk, thanks. So I think I have a similar question that I had to someone. Is the property of the multi-phase medium, could this potentially cause a stalling of the Lyman-alpha photons and potentially still allow some feedback-free galaxies? Or do you don't think, because you don't resolve this there in your simulations, right? I mean, so that it's very tough to simulate in these global simulations. Do you think that this would change your conclusion?
So to me, not really much, in the sense that we find that, for example, so in the simulation, if we change temperature, you still have like velocity, temperature gradient in the simulation. It's not really multi-phase medium, but when you are at such high column density, Lyman-alpha photons scatter anyway. So my feeling is that even in multi-phase medium, probably you still have an effect, but of course...
but they could escape at the far wings, where they actually make very little feedback, right?
Yeah, but again, the column densities are very, very high, so you have to be very far in the wings to really escape. Yeah, again, so Anne was showing the column density of the system. It was like 10 to 20, right, at maximum. And yeah, here, POP3, it could be like the order of magnitudes higher. So, but yeah, of course, it's So Lyman-alpha radiative transfer is a difficult problem by itself, and radiation pressure, it's not hasn't been investigated so much. So to me, it's really interesting to go, step by step and actually check if it's does really matter or not. Of course, yeah, that would be ideal to have proper multi-phase gas. But
Thanks.
All right, we need to move on. Let's thank Daniele.
thank you.